Okay, so welcome back to the last talk of the day. This talk will be given by Chaya Ganesh, who has very recently joined us at Department of Computer Science. So we are part of the same family now, and my relation with her goes back to IIT Madras. So we are actually academic siblings. CPR, I did a PhD with him, and when she did her masters with CPR, and I'm really happy that she joined CSA, and we will probably get to work and collaborate a lot. And she is going to touch upon another very interesting primitive in the area of MPC, zero knowledge. Specifically, so I mentioned about the malicious security, right? So if you had to tackle such stronger kind of adversary, then this is the tool that you need, zero knowledge, okay, which allows a party to prove something without giving any knowledge about the secret statement, the secret proof that it has. Yes, so with that, I will leave the stage to Chaya. The stage is yours.
Thank you, Arpita. So this is supposed to be an introductory talk. What this is not is, it's not a comprehensive survey. Instead, what I'll try to do is present some high-level ideas of some proof systems that are easy enough to present without assuming a lot of prerequisites, and motivate with some statements that arise in important applications in practice. Okay, so let's begin. What is a zero knowledge proof? So imagine we have a prover and a verifier and two differently colored balls that are otherwise identical. And now Bob here claims that he can actually distinguish between these two balls. As far as Alice is concerned, they are completely identical, and she is skeptical of Bob's claim. So what can Bob do to actually prove to Alice that he can actually distinguish between these two? What she can do is she can toss a random coin, and if it comes up heads, she is going to swap the two balls. Imagine Alice doing this behind her back, so Bob doesn't actually see. And if it turns up tails, she doesn't swap, and then she asks Bob, did I swap or not? If Bob can indeed distinguish between these two differently colored balls, he can actually answer this question correctly, and he can say, yes, you did swap. And why is this zero knowledge? Because Alice doesn't actually learn which ball is salmon and which ball is violet, and in her view, all she sees is a random bit that she tossed. We also want the property of a proof, which means that Bob should not be able to convince Alice about a false statement. And here, if you think about it, Bob can actually convince Alice even if he cannot distinguish by simply guessing her random coin. So Bob can cheat with probability half, but with enough repetitions, the probability that he gets lucky can be brought down exponentially. So a little more formally, zero knowledge proofs give us a powerful tool that allows a prover to convince a verifier that a statement is true without revealing anything beyond the validity of the statement. And it should satisfy certain properties like completeness, soundness, and zero knowledge. So what does completeness say? If Bob is claiming that he knows an input w to the function f such that it evaluates to y for some public f and y, then they can interact, and if this is indeed true, Alice should accept. So this is completeness, which says that an honest prover should be able to convince the verifier of a true statement. And what is soundness? If Bob is cheating, a cheating prover should not be able to convince Alice about a statement that is not true, no matter what he does in the protocol. And the property of zero knowledge says if Alice is cheating, if the verifier tries to learn more from the protocol than she is allowed to, then she should not be able to. She should not be able to learn anything more than the truth of the statement. And this is formalized by the simulation paradigm that you heard a little bit in some of the previous talks, but I'm not going to go into the definition. So zero knowledge proofs have a rich theory in cryptography, and now we know that any statement in NP has a zero knowledge proof. And the question really is about efficiency. And when it comes to efficiency in practice, there are a bunch of parameters where we want to optimize one or the other depending on the exact application. And typically we'll be concerned with parameters like the communication complexity or the proof size in the case of a non-interactive proof, the number of rounds of the protocol, the prover computation, verifier computation, is there a setup, do we trust the setup, and so on. And roughly proof system, the techniques that we use to construct proof systems depend on all these different parameters. Like I said, depending on setup, complexity of the prover and the proof, what assumptions we are willing to make, do we want to make non-standard assumptions, is interaction allowed in a given application or not, and what class of languages do we want to prove statements about. I want to begin by talking about a class of protocols that are called sigma protocols, both because they give us efficient proofs, even though for a restricted set of languages. They give a way to obtain efficient zero knowledge for interesting languages that come up typically in applications. And this also gives us a good starting point for constructing proofs for arithmetic circuits, which is the idea behind bullet proofs, which actually gives succinct proofs. Okay, let's begin with an example, which is the Schnorr's protocol for proving discrete logarithms. We have a group of some prime order Q and a generator G that is known, and X here is public, both Alice and Bob know X, and the prover in addition is claiming that he knows W such that X is G to the W. So how can Bob prove this? So Bob chooses a random R, computes G to the R and sends A to Alice. Alice sends a random challenge, which is a bit string that is T bit long, such that 2 to the T is less than Q. And now Bob is going to respond with Z, which is computed as R plus CW, where R is the randomness he chose in the first step of the protocol, C is the challenge he received from Alice, and W is the witness. And now Alice can simply check whether this equation holds, and if it does, she is going to accept, otherwise she doesn't. So here is the protocol just for reference. And does it satisfy completeness? Can an honest prover make verifier accept? So recall the verifier here is going to check whether this equation is true. So what is G to the Z? Z is basically R plus CW. And if we just do the arithmetic, this is actually A times X to the C, and indeed the verifier can accept. So what about soundness? Turns out sometimes membership in a language is trivial. For example, here every group element indeed has a discrete log. So it doesn't mean much for Bob to say that there exists a discrete log. So what we really want is something that is stronger, called a proof of knowledge. And here Bob wants to convince Alice that not only there exists a discrete log, but he knows it. So imagine the prover can actually answer with Z that makes the verifier accept for 2 different challenges for the same first message A. That is, we have A C Z and A C prime Z prime, where both of them are accepting for Alice, which means that these 2 equations hold. Now if we simply divide the 2 equations, we'll get G to the Z minus Z prime is X to the C minus C prime. And since I said these are 2 different challenges, C minus C prime is non-zero, so there exists an inverse, which means we found the discrete logarithm of X to base G, which is simply Z minus Z prime over C minus C prime. So what does this tell us? If the prover can answer 2 different challenges, then we can actually extract the discrete log, which means he must have known the discrete log. So very roughly, the probability that a prover is cheating is when he can only answer 1 challenge for a fixed first message A, and that simply happens with probability 1 over 2 to the T, because T is the length of the challenge. So what about zero knowledge? So if we think about it, imagine C was just a 1-bit challenge, in which case we can easily simulate by simply guessing the challenge bit. But the simulator cannot guess a long string, and we actually want the string to be long because we want the soundness to be good. If it is just a single bit, then we only have soundness half, and then we should repeat and so on. But turns out this protocol satisfies a property called honest verifier zero knowledge, which means that if the verifier actually behaves honestly, this is in a spirit similar to semi-honest adversaries, then this is actually zero knowledge. And how do we simulate? The simulator can simply choose random Z and C and then compute A such that the verification equation is satisfied. And notice that this ACZ has the same distribution as in the real execution. So Sigma protocols will generally follow this template where the prover is going to send a first message that we are going to call A. V sends a random t-bit string. This is what makes it a public coin protocol, which is useful for turning it into non-interactive proofs. And P sends a response Z, and V accepts or rejects based on just this transcript, which is the instance and A, C and Z. And what are the properties of such Sigma protocols? Completeness is natural. This is what we just saw, that is, an honest prover should be able to convince a verifier. And it satisfies a special soundness, which is the proof of knowledge kind of property, which basically says there exists an efficient extractor that, given the instance and two accepting transcripts for the same first message A, and for different challenges C and C prime, will be able to spit out a witness such that X and the witness is in the relation. And the third property is what is called special honest verifier zero knowledge, which says there is an efficient simulator that, when given the instance and the challenge, can output an accepting transcript that is also distributed similar to the real execution. So earlier what we showed was just honest verifier zero knowledge, and this is special because this can simulate for even a given challenge. And later we will see that this is useful when we want to apply different transformations on Sigma protocols. So what can we do with these class of Sigma protocols? Turns out we can do quite a lot of things. We can prove compound statements like AND, OR and subset of statements. And we can also transform a Sigma protocol which is only honest verifier zero knowledge into full zero knowledge. And we can also do this efficiently by taking many statements that we want to prove, construct a compound statement, construct a Sigma protocol for the compound statement, and then apply the transformation. And we can also get zero knowledge proof of knowledge from such Sigma protocols. To prove an AND of many statements, this is rather simple. Let's say we want to prove a bunch of AND clauses. So we want to prove x1 is in the language and x2 is in the language and so on. All the prover has to do is simply run all these protocols in parallel, and what the prover can do is use the same challenge and soundness will still hold. And sometimes we can do better where we can batch the messages that the prover sends for efficiency depending on the exact statement in each of these clauses. The OR of Sigma protocols is more interesting because here we want to prove either x1 is in the language or x2 is in the language and so on. And here for zero knowledge to hold, we cannot reveal which one is true and which one is not. So there is this really nice idea in Kramer, Damgaard and Schoenmakers from Crypto 94 where the idea is as follows. Let's say we want to prove the OR of just two clauses. And let's assume the prover knows the witness for x1 and doesn't know the witness for x2. And now the idea is that if the challenge is known beforehand, then it is easy to cheat by simply simulating. And that's exactly what we're going to do. The prover is going to choose a random C2, which is the challenge that corresponds to the Sigma protocol for the second clause for which he does not know the witness, and just runs the simulator to get a transcript. And for the first clause for which he indeed knows the witness, he computes A1 the way he would do anyway. And these two messages are sent to the verifier. And now the verifier sends a challenge. And what happens here is, again by the soundness property of the Sigma protocol, for a statement for which the prover does not know the witness, there is only one challenge for which he can give an accepting transcript. And now that C2 is chosen, after getting the verifier's challenge C, this completely binds him to the challenge. So now he can set C1 to be C XOR C2, and remember he's already bound to C2 because this is a simulated transcript. And now he sends C1, C2 and the two responses. So Z2 is again the simulated response and Z1 is what he computes. And now the verifier checks that both transcripts are accepting and also that this relationship holds between the challenges. This can also be transformed to prove the OR of many clauses, and they also need not be the same languages. We can actually use proofs for different languages, different protocols for different languages, and combine them together this way. What about K out of NR? What if the prover wants to prove that he knows the witness for K different clauses? Without going into too many details, it's the similar idea. So in the previous transformation, we bound the verifier's challenge for the clause for which he did not know the witness, and we want to do the same thing here. And the idea is to use secret sharing to fix the challenges. What the prover does, it uses the simulator for the statements for which it does not know the witness, and think of these challenges as being evaluations of a polynomial, and this polynomial is going to be determined by the challenge that the verifier sends. So now, after receiving the verifier's challenge, the prover finds the unique polynomial of degree n minus k that passes through these points. These are indices for which the prover has no witness, and where c is the free coefficient. And now the verifier checks that all these challenges lie on the polynomial of the correct degree and does the same thing as before, that all of the transcripts are accepting. So this is a really neat idea, and they do more in the paper where they show how to batch when k is greater than n by 2 more efficiently, and this also works for monotone circuits. So this gives us honest verifier zero knowledge, and more often in practice we cannot assume that the verifier is actually honest. So how do we get full zero knowledge starting from sigma protocols? Again, the reason why we cannot simulate is because if the verifier is not honest, the verifier's challenge can actually depend on the prover's first message. So the idea to transform it into full zero knowledge is to have the verifier commit to the challenge beforehand, and if we use a perfectly hiding commitment scheme, this completely hides the challenge and the prover cannot cheat. So again, we have the following setting: x is the witness. X is the instance, W is the witness, and now the verifier commits to the challenge in the first message, and then prover sends the first message of the sigma protocol. Now we will have the verifier open to the challenge, and the prover checks that the opening is correct, and if yes, responds with the final message. And now the verifier can do the similar check as before. So now we can simulate, because what we can do is we can have the verifier decommit and then rewind and then repeat until the verifier decommits again. But what about proof of knowledge? Did we now break proof of knowledge? Because what a cheating prover can do is choose A depending on the commitment. So remember, for the extractor to work, we wanted two accepting transcripts for the same first message A. And now if we rewind, maybe the prover will send a different A depending on the commitment. So how can we get a proof of knowledge? The idea is to use a trapdoor commitment scheme. And now when the prover sends the third message, it also gives the verifier the trapdoor of the commitment scheme. A trapdoor commitment scheme allows one to equivocate. And now the verifier is going to check that the trapdoor is correct, and the rest is the same as before. And this property is already satisfied by Peterson commitment scheme, which is perfectly hiding, and also the trapdoor is basically the discrete log of h with respect to g. And what did we achieve by this? Now the extractor can learn the trapdoor. It doesn't help the verifier because the verifier has already opened the C before learning the trapdoor. And after learning the trapdoor, the extractor can equivocate to a different challenge and can rewind only up to the point where A is the same. So now we have proof of knowledge, and what we can do, so remember I said the verifier sends a random bit string, which makes this protocol a public coin protocol, which means in the random oracle model we can derive the verifier's challenge as the output of the random oracle without having to interact with the verifier. And this works for, so the example we saw was for discrete log, and this can be extended to prove knowledge of committed value, encrypted value, to prove knowledge of a root, to prove knowledge of, to prove polynomial relationships among committed values, and so on. And in a work by Kramer and later by Maurer, this can be captured, all these classes of sigma protocols can be captured by the language that is knowledge of preimage of a one-way group homomorphism. Anything that can be cast in that language has a sigma protocol. So we have this for algebraic languages, and these are already very useful because they come up a lot in practice. But can we go beyond? Can we have protocols to prove statements about circuits? And the sigma protocol ideas is a starting point. So before I show you some of the ideas, let's introduce this language that is rank 1 constraint satisfaction, which is simply going to be a very convenient representation. And later we will see that we can encode any circuit as an R1CS. So what this says is simply the following: given some public matrices A, B and C, a public vector X, does there exist some secret vector W such that the following is true? This matrix A times the augmented vector X and W. This here is component wise product. So matrix times vector is a vector. So this vector component wise product with this vector, is it equal to this vector? So basically this is the language. I'm saying A, B and C are public matrices. We have a public vector X, and the question is there some W that satisfies this? So why is this useful? Let's see how we can encode any circuit into this R1CS language. Imagine we have this arithmetic circuit here over a field with addition and multiplication gates. And we want our instance to be these public matrices, and the witness is going to be W. And this is the equation that we want to check. The prover wants to prove that it knows W such that this is satisfied. So how can we encode this circuit into these matrices? So what we are going to do is we are going to construct an extended witness, which is going to be the input to the circuit and all the outputs of the multiplication gates. So here I'm going to take these two inputs and the output of this gate and the output of this gate. And this is the vector. This is the extended witness vector. And now if we simply look at these vectors here as A, W, B times W and C times W, and if we look at what this equation says, which remember this is component wise multiplication. So what happens here? This basically gives us all these circuit constraints. So AW component multiplied with PW is basically W1 times W2 is W3, which is the first multiplication gate. W3 times W2 is W4 is the second multiplication gate. So what we are doing is we are capturing these multiplication gates in these matrices, and this is basically going to check that these gates are satisfied. And the matrix has dimensions that depends on the size of the circuit, and so the number of rows is going to be the number of multiplication gates, and the number of columns is going to be the length of the secret input plus the number of multiplication gates. The point is R1CS captures circuit satisfaction, and it's going to be a very useful intermediate language to construct proofs for. So now can we use sigma protocols to prove something about R1CS? So again, remember we have Peterson commitments, which gives us a perfectly hiding commitment scheme, assuming we are in a group of order Q. And this also has the property that it's additively homomorphic. So we can multiply two commitments, and what we'll get is a commitment to the sum of the underlying messages. So now recall we have an R1CS instance, which is the matrices A, B and C. The prover in addition has this witness W. The witness W is a vector. The verifier also knows the public instance, and the prover is claiming that this equation holds, which is the R1CS constraint. And the goal is for us to use sigma protocols to prove this. So what can the prover do? The prover can commit to all of these witnesses. So remember W is a vector, and we can use Peterson commitment to commit to each of these vector elements independently, and sends these bunch of commitments to the verifier. And now these commitments are homomorphic, so everybody can publicly compute a commitment of a linear combination of these W's. A, B and C are public matrices, so we can do that. And now all we have to do, given all these commitments, is to prove relationships among committed values. What kind of relationships? We have commitment to A, commitment to B, commitment to C, and we want to prove that A times B is equal to C. And this I just said we know how to do using standard sigma protocol techniques. And in addition, if we also want to prove that the circuit output wire carries a certain value, that is the last element of this witness vector is say 0, we can also do that by simply proving that the opening of a commitment satisfies some relation, or by just opening it if we want to open it. So we can already use sigma protocols to prove R1CS, which means any arithmetic circuit. But the problem is sometimes we care about proofs that are succinct. That is, proofs where the communication or the proof size is only logarithmic in the size of the statement and the witness. And if we go back to this protocol here, this is not succinct. In particular, we used a linear number of commitments. So here we have commitment to every element in the vector, and the vector was as big as the number of gates in the circuit. And in addition, we have a linear number of proofs because we were proving multiplicative relationships among committed values for sort of every multiplication gate actually. And the prover's complexity is also linear in the size of the circuit. But this is already a starting point for the line of work starting from Bootle et al. And currently what is called bullet proofs of Bunz et al. Which uses this to sort of push the frontier and get proof sizes that are succinct. So the prover will still be linear, and in fact the verification will also still be linear, but the size of the proof is not going to be linear. And let's just see the high level idea. So the first problem was the number of commitments was linear, and that's easily fixable. For the kind of commitments we're thinking about, like Peterson kind of commitments, we already know how to use multi-commitments where one group element can commit to a vector. We don't have to independently commit to each element in the vector. So instead of sending a set of zi's where each zi is commitment to wi, we just compute one group element z, which is a commitment to the entire vector w, where we have this vector, oh I'm sorry, these have to be g2 and these have to be, this is product of gi to the wi, h to the r. So the assumption is that there is a I'll talk about assumptions later, but for now the prover does not know the discrete log relation between these generators. And we don't want the prover to send these generators or the verifier to send these generators because that would already make it linear. So we need a way to generate all these generators so nobody knows the discrete log. Think of using a random oracle or something. Yeah, we'll see in the next slide. Yeah, so sorry about the typo here. This is product of gi to the wi and some blinding factor h to the r. Okay, so that solved the first problem, but we still have proof size which is linear because we still have to prove multiplicative relationships among each of these wi's. So what do we do about that? What bullet proofs does is give a succinct proof that proves things about multi-commitments. And a building block of all these proofs is what is called an inner product proof, which basically does the following. We are given two vectors g and h as long as say the size of the circuit, and two group elements x and y, and the prover wants to prove knowledge of two vectors u and v such that this public group element y is g to the u, h to the v, and x to the inner product of u and v. So what this is saying is, here is a group element, and that group element is sort of a commitment to a very long vector u, a long vector v, and the inner product of u and v. So one group element captures two vectors and their inner product. Okay. So how do we again remember we want succinct proofs. We want to be able to do this in a succinct way. So what is the instance here? We have the vectors g. So whatever is in boldface is a vector. That's as long as the size of the statement. So we have vectors g, h, group elements x and y, and vectors u and v are the witness that the prover has. And what the verifier has is just the generators, the vector of generators g and h, elements x and y. And the prover is claiming that y satisfies this relation. That is, y is sort of a commitment to two vectors and their inner product. And the high level idea is to sort of half the size of the instance and repeat. So now think of the vector u as two halves, the left half and the right half, and the same for v, and in fact the same for g and h. Let's just look at the two halves of all these vectors. And now if we compute y left and y r in the natural way, so recall y was basically a commitment to u, v and the inner product, and now I am saying y left is a commitment to u left, v left and the inner product of u left and v left, and similarly for y right. Now y is actually yl times yr. If you want to take a second to verify this, this y here is yl times yr. And this already tells us where we are going. If we have a way to split this, then the verifier can check that this is true and then repeat the protocol on these two instances, which already have smaller size than what we started with. But the problem is we don't want to recurse on both subproblems, because then again we'll be solving problems on all nodes in our tree. So instead what we want to do is recurse on one instance, and that one instance is determined by a random challenge from the verifier, which we will use to combine the two halves into one instance. And because this combination is going to depend on the verifier's challenge, the prover cannot really cheat. And then at the depth of the recursion, we are going to have just one element here instead of a vector, and then we will use the sigma protocols, the kind of the ones that we saw in the beginning, to be able to prove this. So we have the dimension of everything, of the generators and the instances, and then recurse on one subproblem of that dimension. Okay, so now we have a succinct proof for inner argument, inner product, and what bullet proofs does, which I am not going to show, is how to use inner product for all of R1CS. And a very high level idea is to, if you recall, R1CS had this matrix vector product, and then there was component wise multiplication. And now the idea is to combine all these into one single inner product using a random linear combination, where again the randomness comes from the verifier and in the non-interactive setting from a random oracle, and then we just prove that one random linear combination. Sigma protocols are 3-round protocols, and now we increased it to logarithmic number of rounds by recursing. So we have the instance size and recursed again. But this still remains public coin, and they show that even if it's a logarithmic round protocol, Fiat Shamir can still work and it can be made non-interactive. Okay. What I want to do next is sort of show some ideas for zero knowledge from secure computation. So zero knowledge is already a special case of secure computation, where basically one party has inputs x and w, another party has input x, and one party gets no output, and the output that the verifier gets, which is the output of this function f, is what the output of the relation is, that is 0 or 1. So we can of course use secure computation to instantiate this function, but this is a two-party protocol, which means that it necessarily has to be dishonest majority. So this means that we will inherit all the assumptions and inefficiencies of a dishonest majority protocol. We will revisit this, but for now let's look at this really beautiful idea from ICOS 7, where we get zero knowledge from MPC. So earlier we saw how zero knowledge was a tool to compile MPC that gives us only semi-honest security to full security, where it was a tool to force people to behave honestly by proving that they did things consistent with their input and randomness. Instead, here we will see how to actually obtain zero knowledge from an MPC protocol. This is a really nice idea. So let's say we have this relation R. We can define this n-party functionality, which basically takes the instance X, splits up the witness to n shares, W1 to Wn, and the relation is basically recombining all these shares into the witness and applying the relation that we want to check. And we can use a semi-honest, too secure, perfectly correct protocol to instantiate this and get zero knowledge. So let's say we have this prover here with witness W, and we have an MPC protocol for this function. Now the prover is going to, the prover in his head is going to split up the witness W into many shares using some randomness. And let's say we have 5 parties, so there's a 5-party protocol for this function. The prover is going to virtually emulate the protocol in the head and then commit to the views. So the views is basically a log of everything that happened in the protocol, which includes the input, the communication, and the randomness. And all these views are put inside commitments and sent to the verifier. And now the verifier challenges the prover to open 2 of these views at random. And this was a too secure protocol, so this is okay. And the prover is going to open these 2 views, and now the verifier can check that these 2 views are consistent and that both of these parties output 1. So the verifier is going to accept if the output is 1 for these 2 parties and the views are consistent, that is, the incoming message of this and the outgoing message of this match, and so on. So let's just see why this gives us all the properties of zero knowledge protocol that we want. So this is the protocol to recall. So this gives us completeness because we have, let's say we have a MPC protocol with perfect correctness. Then this is very easy to see. The verifier will indeed accept if it's a true statement. For zero knowledge, if we used a protocol that is too secure, the verifier is going to look at 2 views. So roughly this protocol is going to tolerate corruption of 2 parties, so it's okay for the verifier to look at those 2 views. And for soundness, let's say there is no W such that this relation is 1. Let's also look at when the verifier will accept. The verifier is going to accept if both of these conditions hold. And by perfect correctness of the MPC protocol, if all the views are consistent, then the verifier is going to reject if the output is 0. And if there is no such W, it is going to be 0 and the verifier is going to reject. Otherwise, there is one pair of views at least that is not consistent, and the probability that the verifier is going to open those 2 views is 1 over n choose 2. So this gives us a soundness. Again, looking at zero knowledge as a special case of secure computation, what one can do is take a dishonest majority protocol and optimize it for the special case of zero knowledge. So this is another promising direction to get efficient zero knowledge proofs. I'll show you the JKO which uses the Gabel circuit thing, and where they optimize it for the case of zero knowledge. That's where I'm going, and before I get to that, I want to just give an overview of Yao's gabling and what a gabling scheme is. So let's consider a circuit here. This is an AND gate, and what we want to do is choose 2 random wire labels for each wire in the circuit, where the 0 wire label corresponds to the value being 0 and the 1 label corresponds to the value being 1. And now we can look at the truth table of this gate and look at it in terms of the wire labels. And the idea is to encrypt the truth table of each gate, and by encryption I mean just encrypt the output wire label of each gate according to the logic of the gate. So each output wire label is encrypted using a pair of keys. And now the garbled circuit is just going to be all these encrypted gates. And when evaluating a circuit, one can obtain a garbled encoding, which is one label per wire depending on which value is traversing that wire. And a garbled evaluation allows one to obtain only one ciphertext from all these ciphertexts in the garbled gate. And the result of the decryption is going to be the wire value that corresponds to the value on the outgoing wire. So this is sort of the syntax of a garbled circuit. I don't want to dwell on it, but I want to just mention what the properties are. So we want privacy, which means that given a garbled circuit, a garbled input and decoding information, it should reveal nothing beyond the output of the circuit. And we also want authenticity, which says given a garbled circuit and the garbled input without the decoding information, then the adversary cannot find a garbled output in any way other than evaluating the garbled circuit. Okay, so we can use garbled circuits to obtain two-party secure computation. Let's say Bob here has input X, Alice has input Y. Bob just garbles the circuit, sends the garbled circuit, the garbled input corresponding to input X, and the output wire labels to Alice. And now they run an oblivious transfer protocol. OT is this primitive where we have a receiver, the sender has two secrets, the receiver has a choice bit, and OT allows the receiver to pick up the chosen secret. So here we have Alice who uses as input her input to the function, and OT basically allows her to pick up the garbled inputs that corresponds to her input. And now she can evaluate this garbled circuit and use the output wire labels to decode and send the output to Bob. In this work by JKO in 2013, they showed how to base zero knowledge on garbled circuits in an efficient way. And the observation is that zero knowledge is a special case of secure computation where the verifier has no input, or rather the verifier has no private input. So now the Bob here, who is the prover, has X and W such that f of XW is 1, and Alice has X and no secrets. And a way to obtain zero knowledge is by having the verifier garble this circuit. And now they run OT again, where Bob uses the witness to pick up the wire labels corresponding to the witness in the circuit. And Bob can now evaluate the garbled circuit using the garbled inputs and then commit to the garbled output. So we don't want Bob to send the output, because if the verifier is malicious, this garbled circuit could be constructed in a malicious way. It could simply reveal the witness. So what the prover does is just commit to the garbled output, and now the verifier is going to open the garbled circuit and show that this circuit garbles the correct function. And if this is indeed a garbling of the correct function, the prover is going to open the commitment here. And now the verifier can check that this garbled output corresponds to the one label, and if yes, she accepts. So we got zero knowledge using only one garbled circuit. Typically we need more garbled circuits to get malicious security, and this is because we can open the same garbled circuit that was evaluated, again because the verifier has no secrets. I'm pushing some things under the rug here. We actually need a committing OT, a sender committing OT to prevent some kind of selective failure, but that's not important. So now we have zero knowledge from garbled circuits. We have zero knowledge from MPC in the head. Sometimes in applications we want really succinct proofs. So bullet proofs gave us logarithmic size proofs. But sometimes we want constant size proofs and efficient verification. So bullet proofs did not give us efficient verification. The verifier still ran in time linear in the size of the circuit. So ZK snarks, which stand for zero knowledge, succinct, non-interactive arguments of knowledge, yield really succinct proofs and efficient verification. And the best known ZK snarks today have some kind of setup with varying degrees of trust placed in the setup, and the proof can be as small as 3 to 6 group elements, And the verifier is also succinct in that it only needs 3 pairings and number of exponentiations that only depends on the public output. What I want to do for the rest of the talk is to sort of show proofs for composite statements, which are the kind of statements that arise in important applications. So what is a composite statement? It's a combination statement that consists of algebraic and non-algebraic components. And this shows up in practice. For example, I'm going to look at anonymous credential applications. So imagine a setting where we have a certificate authority who is going to issue credentials to users. And the user is going to use this credential later to obtain services by proving properties about himself to a verifier who can be thought of as a merchant or a service provider. So the user has all these attributes, name and citizenship and so on, and the authority issues credentials by certifying all these attributes. And later, if Bob wants to prove something about his attributes, he can of course simply claim certain statements and show these signed attributes. But this also reveals certain other information that we don't want to reveal. So what we want is for Bob to be able to prove things about his attributes without revealing anything else. So if Bob wants to prove that he's older than 21 and resides in New York, that's all Alice should be able to learn. So anonymous credentials have a lot of work, starting from the work of Chaum, and most known credential systems are based on Sigma protocol proofs, the kind of ones we saw. And practical approaches to credential systems like Microsoft's uProve and IBM's IDMX follow a rather standard template, which has the user commit to the attributes and then prove in zero knowledge knowledge of signature on the committed attributes, and then prove again in zero knowledge that the committed attributes satisfy a certain policy. And now, to be able to prove knowledge of signature on a committed message, this means that the issued credential is a specially formed signature to be able to use a Sigma protocol to prove knowledge of signature. And if we want to base credentials on standard signatures, for example, if we want to use existing infrastructure like RSA, PKCS, then how does this work? If we want to base privacy preserving credentials on existing signatures. If we look at RSA, for instance, if we have message M and signature sigma and want to verify that hash of M is sigma to the E mod N, this involves verifying an exponentiation, computing an exponentiation in an RSA group and a hash function. And this is a composite statement, and ideally for efficiency reasons, we want to be able to use zero knowledge proofs that work well for algebraic statements, for the algebraic part of the statement, and proof systems that work well for circuit representations for the hash part of the statement. And now we also want to combine them in a way so that the prover does not cheat by using two different witnesses in the two different proof systems. A building block to get proofs for composite statements is constructing proofs on committed values. And what this means is now we augment the relation to include some public commitment, and we prove what we proved earlier together with the witness is actually inside a public commitment. And why is this useful? Because now we can use this commitment to switch proof systems in any composite statement that we have, and the public commitment sort of gives consistency across the witnesses used in different proofs. So if we have proof systems on committed values, how can we apply this in the credential application that we just saw? So imagine we have attributes M and some sort of signature, imagine a standard signature, and the verifier is also in possession of a public commitment to M. Now the prover can give a zero knowledge proof of knowledge of the signature on M, and then a sigma protocol that M satisfies some algebraic policy, and then a proof that works well for a circuit representation of some function f, that f of m equal to 1 for some non-algebraic policy. And now we have that these properties that are being proved about M and the signature, the proof of knowledge of the signature on M is indeed on the same M, which is tied together by this commitment here. So we can have, so I only have 10 minutes left, so I'm going to skip some of them. But what I want to show is we can build the JKO protocol that we just saw. We can easily take that protocol and modify it to get a garbled circuit based zero knowledge on algebraically committed inputs, and then use that algebraic commitment to switch to sigma protocols. So remember, this was the JKO protocol. At a very high level, so now we have this additional public commitment, and think of this as an algebraic commitment that we later want to use sigma protocols to prove things about. Instead of just garbling this circuit F, the verifier is going to make an augmented circuit that includes a one-time MAC key A and B, and now this augmented circuit is going to compute F of M together with the one-time tag on the input M. And now we do the same thing as before. The garbled circuit is sent to the prover. We have OT, the prover commits to the output label, and now the verifier is going to send decoding information corresponding to just the tag part of the output, and the prover can decode this to obtain the one-time MAC on M, and what the prover will do is commit to this tag using the same commitment scheme as the commitment to M. And now the verifier opens the garbled circuit, the prover verifies, opens the commitment to this output wire label, and now to tie things together, there is a sigma protocol proof that T is actually the correct one-time MAC on M, where we have a commitment to T, a commitment to M, and after opening the garbled circuit, A and B are public values. So this is a linear relationship among committed values, which we saw how to do. We can also make the observation that we don't actually have to compute a one-time MAC inside the circuit, and MAC is sort of for free because the OT keys already give a MAC on the bits of the input. But I'm going to skip this. So zero knowledge on committed values, we saw how to do that for the garbled circuit based zero knowledge proof. If we think about bullet proofs again, it already gives sort of naturally for free proofs on committed values, where we can think of R1CS as being augmented with auxiliary inputs, and they were already using Peterson commitments, which lend themselves well to proving things on committed values. We also know how to construct some kind of snark schemes on algebraically committed values. There is also this work called Lego snark, which shows how to put different snarks together in a modular way while keeping the succinctness of the intermediate state. And there is also work that shows how to do MPC in the head kind of proofs on algebraically committed values, so we can switch between Zikabu and Sigma protocols. And what I didn't say is a lot, because there is a lot of work here. There is a lot of approaches to get practical zero knowledge, which offers different trade-offs under different assumptions, each suited in different applications. And there is really no one scheme that is suited for all applications. I'll stop here, and I'm happy to take questions. So if we use Sigma protocols, they are already based on number theoretic assumptions, and they are not, but MPC in the head is. I'm sure there are, I didn't talk about them. Yeah, LWE would be a candidate for post-quantum secure proofs.
Yeah, any other questions? Okay, so if there are no more questions, so we would like to end today's program, and here's a small token of gift. Thank you.